What if everything we think we know about ancient technology is only half the story? Picture a world where mechanical computers existed thousands of years before silicon chips and digital screens, where gears turned with mathematical precision and bronze hands pointed to the movements of planets with eerie accuracy. This isn't some alternate history or lost Atlantis myth. It's the reality hidden in plain sight, buried in museum archives and crumbling manuscripts. From the shores of ancient Greece to the bustling markets of medieval Baghdad, civilizations we often label as primitive were engineering devices so advanced they could rival the gadgets we use today. Take a moment to consider your smartphone, a pocket-sized supercomputer that tracks time, predicts weather, and even guides you home. Now imagine holding an object just as sophisticated and crafted, not with microchips, but with hand-carved cogs, calibrated to track lunar eclipses or chart the paths of stars. Sounds impossible. That's exactly what historians thought until they stumbled upon artifacts like the Antikythera mechanism, a 2,000-year-old device often called the world's first analog computer. Its intricate bronze gears could predict celestial events decades in advance with a precision that would make modern engineers pause. And it's just one of countless examples where ancient innovation mirrors or even surpasses our own. This video is a passport to those forgotten marvels. We're diving deep into 25 ancient technologies that functioned like modern computers, each one a testament to human creativity that defies the boundaries of time. These weren't just tools, they were revolutions carved in stone and metal, solving problems we still grapple with today, from navigating vast oceans to unlocking the secrets of the cosmos. Why does this matter? Because every gear, every etched calculation rewrites the narrative of progress. It's not a straight line from simple to advanced. It's a spiral where genius emerges in unexpected places, then vanishes, only to be rediscovered centuries later. So if you've ever wondered how the past whispers to the present, or how civilizations without electricity achieved the unimaginable, you're about to uncover answers that will leave you in awe. The journey starts now. Buried beneath the waves off the coast of a tiny Greek island for over 2,000 years, the Antikythera mechanism lay waiting a silent witness to an ancient technological revolution. When sponge divers stumbled upon its corroded fragments in 1901, they had no idea they'd unearthed what scientists would later call the most sophisticated mechanical device of the ancient world. At first glance, it might look like a lump of oxidized bronze, but beneath that green patina hid a labyrinth of interlocking gears, some as thin as coins, others precisely cut with teeth numbering in the dozens. This wasn't just a clock or a calendar. It was a cosmic calculator capable of predicting the positions of the sun, moon, and 5 known planets with staggering accuracy. What makes this device so extraordinary isn't just its complexity, but the sheer ambition behind it. Imagine a civilization without telescopes, without printed star charts, yet able to model the irregular motions of the moon or forecast solar eclipses years in advance. The mechanism's dials could even account for the Saros cycle, a repeating 18-year pattern of eclipses, proving the Greeks understood celestial mechanics on a level that wouldn't be matched again until the Renaissance. And here's the real shocker: every calculation was performed mechanically. Turn the hand crank, and those tiny bronze gears would whirl into motion, aligning pointers across engraved scales like a celestial symphony conducted in metal. But how did they do it? The secret lies in centuries of meticulous observation. Greek astronomers like Hipparchus had already mapped the heavens, noting how planets sometimes seemed to slow down or reverse course, what we now call retrograde motion. The Antikythera mechanism's creators didn't just know these patterns, they engineered a way to replicate them physically. One gear, for instance, uses an ingenious offset pin and slot designed to mimic the moon's elliptical orbit, a feature so advanced it feels almost anachronistic. This wasn't guesswork, it was precision engineering built on a foundation of mathematical theories so refined they echo in modern algorithms. Perhaps most haunting of all is what the mechanism suggests about lost knowledge. Surviving texts from antiquity never mention devices like this, yet the craftsmanship implies it couldn't have been unique. Was there once a workshop somewhere in the Mediterranean where artisans and astronomers collaborated on machines that blurred the line between science and art? The Antikythera mechanism forces us to rethink history's timeline not as a straight march from simple to complex, but as a web of brilliance where innovations rise, vanish, and sometimes resurface when we least expect them. Buried in the sands of Mesopotamia, a humble clay jar no taller than your hand holds a secret that could rewrite the history of electricity. Known as the Baghdad Battery, this unassuming artifact, a terracotta pot housing a copper cylinder and an iron rod, has sparked fierce debates since its discovery in the 1930s. Dating back to around 250 BCE, it predates Alessandro Volta's famous battery by nearly 2,000 years. At first glance, it looks like nothing more than an ancient storage vessel. But the moment you pour an acidic liquid like vinegar or grape juice into it, something remarkable happens. The jar becomes a functioning electrochemical cell, capable of producing around 1 volt of electricity. That's enough to power a small LED or create a tingling sensation on the skin, hardly enough to light a city, but proof that the basic principles of electricity were understood far earlier than we ever imagined. So what was this ancient power source used for? One compelling theory suggests it could have been employed in electroplating, a process where a thin layer of gold or silver is bonded to another metal using an electric current. Artisans in Mesopotamia were known for their intricate gold-plated objects, and while traditional methods like mercury gilding existed, the Baghdad Battery offers a tantalizing alternative. Imagine a craftsman dipping a statue into a gold solution, then connecting it to one of these jars. Over time, the current would slowly deposit gold onto the surface, creating a flawless, shimmering finish. It's a technique that wouldn't be widely documented until the 19th century, yet here's evidence it might have been practiced in the shadows of ziggurats. But not everyone is convinced. Skeptics argue that if these were truly batteries, why have we never found wires or other components to complete the circuit? Why no written records describing their use? It's a fair point, but absence of evidence isn't evidence of absence. Perhaps these devices were rare, their knowledge guarded by a select few. Or maybe their purpose was entirely different. Some researchers propose they were used for medicinal purposes, delivering mild shocks to relieve pain, much like an ancient form of electrotherapy. The Greeks and Romans wrote about using electric fish to numb ailments. Could the Baghdad Battery have been a more controlled version of the same idea? What's undeniable is the design itself. The copper and iron combo, separated by an insulating asphalt plug, mirrors the basic structure of a modern galvanic cell. Even the choice of electrolyte fits vinegar, common in the region, would have been the perfect conductive liquid. Coincidence, maybe, but when you line up the clues, it's hard to dismiss the possibility that someone, 2 millennia before Volta, stumbled onto the secret of harnessing electricity. Whether for plating, healing, or some forgotten ritual, the Baghdad Battery stands as a haunting reminder that innovation isn't always linear. Sometimes it flickers to life in the unlikeliest of places. only to fade into obscurity, waiting for the right moment to shock us awake. The Phaistos Disk sits in a quiet museum case, its clay surface spinning a mystery that has baffled scholars for over a century. Unearthed in 1908 from the ruins of a Minoan palace on Crete, this 4,000-year-old artifact is no larger than a dinner plate, yet its spiraling script, 45 distinct symbols stamped in perfect rows, has resisted every attempt at translation. Unlike the Rosetta Stone, with its parallel Greek and Egyptian scripts offering a key to comprehension, the Phaistos Disk stands alone, its symbols whispering a language lost to time. What's striking isn't just the enigma of its message, but the method of its creation. Each symbol was pressed into the clay using individual stamps, making this the earliest known example of movable type, a technology that wouldn't reappear in Europe for another 3,000 years. Who were the people who crafted such a precise system? The Minoans, a civilization renowned for their vibrant frescoes and labyrinthine palaces, clearly valued more than just art and architecture. The disk's uniformity hints at something extraordinary, a standardized script, possibly mass-produced for administrative or religious purposes. Imagine a room full of scribes, each pressing these symbols into clay tablets to record trade inventories, sacred hymns, or even royal decrees. The very existence of such a system suggests a society with levels of bureaucracy and communication that rivaled far later empires. Yet without a single other example of this script found anywhere else, the disk remains an island of intrigue in an ocean of silence. Then there's the question of its purpose. Some researchers see it as a form of proto-writing, a bridge between pictorial symbols and true alphabets. Others propose it could be a musical score, with the spiral representing a melody played on ancient instruments. The most tantalizing theory that it's a kind of Bronze Age punch card, a coded set of instructions meant to be read by a machine, perhaps one that no longer survives. After all, if the Antikythera mechanism proves the ancients could build complex gear-driven devices, why not a primitive data reader? What's undeniable is the disk's eerie modernity. In an era when most writing was carved laboriously by hand, the Minoans were experimenting with reusable type, a concept that wouldn't flourish until Gutenberg's printing press. The symbols themselves, men running, helmets, shields, even a beehive, feel like fragments of a story we'll never fully hear. Every attempt to crack the code, from statistical analysis to AI pattern recognition, has hit the same wall. Without a bilingual reference or more examples, the disk guards its secrets fiercely. Perhaps that's the real lesson of the Phaistos Disk. It's not just a puzzle to solve, but a humbling reminder of how much history remains just beyond our grasp. For all our technological advances, we're still peering through a keyhole into the past, catching glimpses of ingenuity that challenge our assumptions about progress. The Minoans didn't just leave us an artifact, they left a challenge, daring us to imagine a world where innovation flickered brightly, then vanished, waiting to be rediscovered. Deep in the forests of what is now Germany, a relic was unearthed that would shatter our understanding of Bronze Age Europe. The Nebra Sky Disk, a shimmering bronze plate no wider than a bicycle wheel, gleams with gold inlays that trace the exact positions of stars, the crescent moon, and even a cluster believed to be the Pleiades. Dating back to around 1600 BCE, this isn't just art, it's the oldest known portable representation of the cosmos, a celestial map forged in metal. Unlike static cave paintings or rudimentary carvings, the disk was designed to be held, rotated, and studied, a tool as functional as it was sacred. What makes the Nebra Sky Disk so revolutionary is its precision. The gold arcs along its edges aren't decorative, They mark the solstices, calculating the angle between sunrise and sunset with an accuracy that would have guided planting and harvests for generations. Farmers could hold the disk up to the horizon, aligning its markers with the sun's path to predict the turning of seasons. But this wasn't just a farmer's almanac. The inclusion of the Pleiades, a star cluster tied to agricultural cycles across ancient cultures, hints at something deeper, a fusion of myth and mathematics. In Babylonian texts, these stars signaled the start of the planting season. In Greek lore, they were the seven sisters. The disk's creators, though separated by continents and centuries, shared this cosmic language, weaving practical astronomy into the fabric of their beliefs. Yet the disk's true genius lies in its adaptability. Archaeologists discovered that it wasn't made in a single era but evolved over centuries. Later modifications added a solar barge, a symbol of the sun's nightly journey through the underworld, transforming it from a simple calendar into a narrative of creation. This wasn't just technology, it was a living document, updated like software to reflect new discoveries or shifting beliefs. Imagine a community gathering under the stars, passing the disk from hand to hand, each generation adding its own layer of meaning to the bronze canvas. The Nebra Sky Disk forces us to rethink the boundaries between tool and talisman. Modern GPS relies on satellites, the disk used constellations. Both serve the same purpose: to navigate, to predict, to connect humanity to the rhythms of the universe. In a world without written records, this metal map was a library, a church, and a compass rolled into one. Its survival is a miracle, a whisper from a time when science and spirituality weren't opposites, but partners in deciphering the heavens. Imagine a chariot that never loses its way, a vehicle so advanced, it could guide travelers across vast deserts without a single landmark in sight. The south-pointing chariot, crafted in ancient China over 4,600 years ago, wasn't pulled by magic or myth. It was powered by pure mechanics, a masterpiece of gears and ingenuity that defied its time. At first glance, it resembled any other ornate carriage of the Han dynasty, but hidden within its wooden frame lay a system of interlocking differential gears that performed an astonishing trick. No matter which way the chariot turned, a figure mounted on top would always point south. This wasn't just a clever party trick, it was the world's first non-magnetic compass, a navigational breakthrough that predated the magnetic compass by centuries. How did it pull off this feat? The secret lay in its gear ratios. Each time the chariot made a turn, the wheels would rotate at slightly different speeds, thanks to a sophisticated arrangement of gears. These subtle differences were then transferred through a series of interconnected mechanisms, adjusting the position of the pointer to compensate for the change in direction. Picture it like a mathematical dance, every movement calculated, every rotation accounted for, ensuring the figure on top remained locked to the southern axis. It's the same principle modern cars use in their differentials today, allowing wheels to rotate independently while maintaining control. The ancient Chinese didn't just invent a curiosity, they unlocked a fundamental concept in mechanical engineering that would echo through millennia. But why south? In Chinese cosmology, south wasn't just a direction, it was a symbol of power, prosperity, and cosmic harmony. Emperors faced south when holding court, aligning themselves with the heavens. The chariot's unwavering pointer wasn't just a tool, it was a cultural statement blending science with spirituality. Some historians speculate these devices were used in royal processions, a dazzling display of imperial ingenuity. Others suggest they might have guided military campaigns across unfamiliar terrain, giving armies an edge no enemy could replicate. What's most remarkable is how closely the chariot's logic mirrors modern navigation systems. Today's inertial guidance technology, used in everything from submarines to spacecraft, relies on similar principles, tracking movement and adjusting direction without external references. The Chariot's gears were essentially an analog computer, processing physical inputs to solve a real-time problem. It's a humbling thought. The same mechanical wisdom that guided ancient travelers through dust storms and mountain passes now helps rockets navigate the void of space. Yet for all its brilliance, the south-pointing Chariot remains shrouded in mystery. No original survives, only descriptions and later reconstructions. Did it inspire the magnetic compass, or was it a parallel innovation lost to time? The answer might lie buried in some forgotten tomb or crumbling manuscript. Until then, the Chariot stands as a testament to a truth we're only beginning to grasp, that the ancient world was far more mechanically audacious than we ever dreamed. Hero of Alexandria gazed at the flickering flames in his workshop, envisioning a weapon that could harness fire itself as a controlled force. The result was his fire syringe, a deceptively simple bronze tube that became one of antiquity's most fearsome innovations. When soldiers pumped its piston with sudden force, compressed air would shoot through the narrow nozzle, igniting oil or resin into a searing jet of flame. This wasn't just a torch, it was precision pyrotechnics, allowing warriors to strike targets over 30 feet away without exposing themselves to enemy arrows. The brilliance of Hero's design lay in its marriage of physics and practicality. By exploiting the relationship between pressure, airflow, and combustion principles that would later define internal combustion engines, he turned basic metallurgy into a battlefield revolution. But the fire syringe's legacy extends far beyond warfare. Peer closer at its mechanics, and you'll spot the embryonic DNA of modern technology, that piston and cylinder arrangement. It's the same foundational concept behind everything from bicycle pumps to diesel engines. Hero essentially created the world's first pneumatic actuator, proving that air itself could be harnessed as a power source. Historians suspect these devices might have doubled as ceremonial tools in temples, where priests used controlled flames to awe worshippers, an early example of technology serving both sacred and secular purposes. What's often overlooked is how Hero documented his inventions. His manuscripts read like ancient patent filings, complete with detailed diagrams and operational theories. He didn't just build devices, he systematized knowledge, ensuring future generations could iterate on his ideas. This meticulous approach mirrors modern engineering practices, where breakthroughs depend as much on shared documentation as on individual genius. Yet for all its sophistication, the fire syringe also reveals a paradox of ancient innovation. While its military applications were devastatingly effective, the broader potential of pneumatics remained largely untapped for centuries. Imagine if Hero's contemporaries had adapted his principles for irrigation pumps or mining equipment, how differently might industrialization have unfolded? The fire syringe stands as both a triumph and a cautionary tale, reminding us that technological progress isn't inevitable. It requires visionaries to see beyond immediate uses, to envision the ripple effects of a single spark. The Roman dodecahedrons emerge from history like geometric ghosts, 12-sided bronze puzzles scattered across Europe, silent witnesses to a mystery we've yet to solve. Unearthed in places as far apart as Britain and Hungary, these palm-sized objects gleam with mathematical perfection, each pentagonal face precisely sized, every corner studded with hollow knobs, their surfaces devoid of inscriptions or wear marks that might betray their purpose. For over 300 years, archaeologists have scratched their heads over these artifacts, spinning theories as varied as the dodecahedrons themselves. Were they celestial calculators, their knobs aligning with stars, Could they have been ingenious surveying tools, measuring distances or land angles with their symmetrical geometry? One particularly creative hypothesis suggests they were knitting aids, the knobs guiding thread to craft intricate gloves, except no traces of fiber or wear support the idea. What makes these objects so tantalizing isn't just their obscurity, but their sheer ubiquity. Over 100 have been discovered, often in military outposts or wealthy homes, hinting at a standardized purpose important enough to mass produce. The Roman Empire wasn't known for frivolous curiosities. Every artifact had a function, from aqueduct valves to surgical tools. The dodecahedron's precision implies they weren't decorative. Their hollow knobs and varying hole sizes suggest something was meant to pass through them, perhaps threads, liquids, or even beams of light. One experiment demonstrated that when sunlight strikes the object at certain angles, the holes cast distinct shadows that could mark seasonal changes, like a portable sundial with 12 faces. Yet without a single reference in Roman texts or murals, their true role remains as elusive as smoke. Perhaps the most haunting possibility is that we're missing a key piece of context, a cultural lens that would make their purpose obvious. Imagine someone 2,000 years from now uncovering a modern corkscrew without any knowledge of wine bottles. The dodecahedron might be something equally mundane, its brilliance lying not in complexity, but in solving an everyday problem we no longer recognize. Or it could represent a technology so niche, so tied to a lost ritual or trade, that its logic died with its last user. What's undeniable is the craftsmanship. Casting such symmetrical forms in bronze required advanced metallurgical skill, and the absence of tool marks suggests they were made with reusable molds. This wasn't backyard tinkering, it was industrialized production, hinting at a demand we can't yet fathom. The dodecahedrons challenge our obsession with labeling ancient artifacts as either practical or ceremonial. What if they were both, a sacred object for augurs to divine the future, or a merchant's gauge for sizing precious stones? Their silence is a lesson in humility, reminding us that history's most stubborn riddles aren't always those of capability, but of context. For all our satellites and supercomputers, we're still peering through a keyhole into the Roman mind, left to wonder at a 12-sided enigma that refuses to yield its secrets. High in the jungles of Mesoamerica, the Maya crafted a timekeeping system so precise, it could pinpoint celestial events millennia before or after their own era with uncanny accuracy. The long count calendar wasn't just a way to mark days. It was a sprawling mathematical universe built on a base 20 numerical system that incorporated the concept of 0 centuries before it appeared in Europe. Picture a cosmic clock with interlocking gears of time, where each rotation represented not just years but epochs. At its heart lay the Bakton, a unit equivalent to 144,000 days, or roughly 394 of our modern years. Stack these Baktons like layers of a pyramid, and suddenly you're tracking time across spans that dwarf human lifespans, aligning planetary cycles with mythological narratives of creation and renewal. What set the Maya apart wasn't merely their ability to calculate, it was their vision of time as a living, cyclical force. Unlike our linear Gregorian calendar, their system wove together multiple cycles. The 260-day Tzolk'in, used for ritual and agriculture, harmonized with the 365-day Hob, creating a 52-year calendar round that synchronized sacred and solar time. But the long count went further, stretching into the millions of days, allowing priests to predict eclipses, Venus's appearances, even the theoretical start and end of cosmic eras. Modern astronomers have found their calculations for lunar phases to be off by just 33 seconds per month, a margin of error that would take thousands of years to accumulate even a single day's discrepancy. The secret to this precision, a numeral system as elegant as it was revolutionary. While medieval Europe still struggled with Roman numerals, Maya scribes used just 3 symbols, a dot for 1, a bar for 5, and a shell glyph for 0. This allowed them to perform complex calculations with positional notation, the same logic underpinning modern computing. A Mayan priest could subtract dates across centuries or project solstices forward 10,000 years as effortlessly as we might tally groceries. Their 0 wasn't just a placeholder, it was a philosophical leap, acknowledging the void as a measurable concept. Yet the calendar's true genius lay in its duality. Each date carried both mathematical and mythological weight. The much misunderstood end of the 13th Bacton in 2012 wasn't a doomsday prophecy. It was the reset of a cosmic odometer, a moment of renewal akin to our New Year's celebrations. The Maya saw time as a spiral where history's patterns repeated in grand, rhythmic waves. Their calendar didn't just track days, it encoded a worldview where astronomy, mathematics, and spirituality converged. Today, we use atomic clocks and supercomputers to map celestial motion. The Maya achieved similar feats with obsidian tools and bark paper, proving that technological sophistication isn't about materials, it's about imagination. Their calendar stands as a monument to a civilization that looked at the stars and didn't just see points of light, but a celestial blueprint waiting to be decoded. Every time we check our digital calendars, we're echoing a quest that began in jungle observatories 2,000 years ago, the human drive to tame time itself. In the arid landscapes of Rajasthan, where water was as precious as gold, ancient engineers devised a solution that transcended mere utility. They built stepwells that doubled as celestial calculators. Chand Baori, with its 3,500 perfectly symmetrical steps descending 13 stories into the earth, isn't just a feat of architecture, it's a stone and mortar computer. Each step, each corner, each shadow was calibrated with intentional precision, turning the entire structure into a giant sundial and astronomical observatory. When the sun reached its zenith during summer solstice, sunlight would penetrate the well at a specific angle, illuminating a carved marker that signaled the arrival of monsoon rains. The steps themselves acted as a calendar, their shadows shifting predictably with the seasons, allowing priests to track the solar year with astonishing accuracy. But the genius of these stepwells goes beyond simple timekeeping. The geometric arrangement of their staircases, often forming intricate fractal patterns, encoded mathematical principles that mirrored the cosmos. At Adalaj Vav, for instance, the play of light and shadow during equinoxes creates a perfect alignment between certain steps and the sun's position, a phenomenon that repeats like clockwork every year. This wasn't just artistry, it was applied astronomy. Farmers relied on these alignments to know when to sow crops, while priests used them to determine festival dates, blending practicality with spirituality in a way that feels almost poetic. What's truly remarkable is how these structures functioned without a single moving part. Unlike the geared mechanisms of the Antikythera device or the rotating chariots of China, the stepwells achieved their calculations through pure architecture. The well's depths acted as natural hygrometers, the cooler air at the bottom condensing moisture earlier in the dry season, hinting at coming rains. Even the sound of water echoing up the steps was said to change subtly with atmospheric pressure, offering an early form of weather prediction. Yet the stepwell's legacy extends beyond their technical brilliance. They were communal supercomputers where every villager could read the signs. Women gathering water would note the shadow positions. Children playing on the steps absorbed celestial rhythms through sheer repetition. This was knowledge democratized, etched into the very stones people walked on daily. In an age before paper or widespread literacy, the stepwells made advanced astronomy accessible to all, encoding complex data into a language of light, space, and movement. Today, as modern meteorologists rely on satellite arrays and supercomputers to model climate patterns, the stepwells stand as a testament to an older, quieter kind of genius. They remind us that technology doesn't always need circuits or code sometimes. The most powerful calculations are carved into the earth itself, waiting for the right moment to reveal their secrets. The Viking sagas whispered of a mystical tool, a sunstone that pierced through clouds and fog, guiding longships across trackless oceans with uncanny precision. For centuries, historians dismissed these accounts as mere legend, until a chance discovery in a shipwreck off the coast of Alderney revealed a small, milky white crystal nestled among navigation tools. This wasn't just any stone, it was calcite, a mineral with extraordinary optical properties that could literally unveil the sun's position even on the gloomiest days. How did it work? Calcite's secret lies in its ability to polarize light. When held toward the sky and rotated, the crystal filters sunlight into distinct patterns, creating twin beams that align only when facing directly toward the hidden sun. By marking this exact angle, Viking navigators could triangulate their position with remarkable accuracy, turning a simple rock into the world's first optical GPS. What's staggering isn't just the ingenuity of the method, but the sheer audacity of the voyages it enabled. While medieval Europe clung to coastal routes, terrified of losing sight of land, Viking ships were crossing the North Atlantic, a feat equivalent to navigating by starlight alone. The sunstone didn't just point north like a magnetic compass. It mapped the sun's arc across the sky, allowing sailors to maintain their latitude with scientific precision. Researchers testing replicas in Arctic conditions found they could determine the sun's location within 5 degrees, even when it was physically obscured by storm clouds or lingering below the horizon during polar twilight. Yet the true brilliance of this technology was its simplicity. Unlike the intricate gearwork of the Antikythera mechanism or the monumental scale of Mayan calendars, the sunstone required no moving parts, no complex calculations. It leveraged a natural phenomenon anyone could learn to interpret with minimal training. A navigator might hold the crystal up, rotate it slowly until the light patterns matched, then scratch a line along the ship's rail to mark the angle. Over hours, these marks would trace an invisible map in the wood, revealing the ship's course as clearly as a modern chart. But here's the twist: the sunstone wasn't foolproof. On completely overcast days or during the long twilight of northern winters, even calcite had its limits. That's where Viking wayfinding skills truly shone, a layered system combining the stone with other techniques. They studied wave patterns, noted the flight paths of seabirds, even tasted seawater to detect glacial melt from distant lands. The sunstone was just one tool in a vast cognitive toolkit, proving ancient navigation was as much about intuition and accumulated wisdom as it was about technology. Modern experiments have only deepened the mystery. Some researchers argue that other crystals like cordierite or tourmaline could have achieved similar effects, suggesting the Vikings may have used whatever polarized stones their lands provided. Others point to Norse myths describing sun boards, wooden discs with notches that, when paired with the sunstone, could function like a primitive sextant. What's undeniable is that this technology predated Europe's adoption of the magnetic compass by centuries, offering a glimpse into a maritime culture that viewed the natural world as both ally and instructor. The sunstone's legacy lingers in unexpected places. Today's pilots still learn to navigate by polarized light in emergencies, and modern drones use similar principles for orientation. But perhaps its greatest lesson is one of perspective. Sometimes the most advanced technology isn't the one with the most parts, but the one that listens closest to nature's whispers. The Vikings didn't conquer the Atlantic through brute force, they did it by learning to read the sky's hidden language, one beam of polarized light at a time. Imagine a world where earthquakes could be detected before the ground even began to tremble, where an ornate bronze vessel sat in the emperor's court, silent and still, until disaster struck hundreds of miles away. In the year 132 CE, Chinese inventor Zhang Heng unveiled precisely such a marvel, the world's first seismoscope. This towering bronze masterpiece, shaped like an inverted vase and adorned with 8 sinuous dragons, wasn't just decorative. It was a mechanical oracle capable of sensing distant quakes with eerie precision. Each dragon clutched a bronze ball in its jaws, poised above the open mouth of a corresponding frog. When an earthquake's vibrations reached the device even from as far as 400 miles away, an internal pendulum would swing, triggering one of the dragons to release its ball with a resonant clang into the waiting frog below. The direction of the fallen ball pointed unerringly toward the epicenter, giving officials crucial time to dispatch aid or prepare for aftershocks. What set Zhang Heng's invention apart wasn't just its functionality, but the sheer elegance of its engineering. Hidden inside that bronze shell lay a sophisticated system of weighted levers and inertia-driven mechanisms, principles that wouldn't reappear in Western seismographs until the 19th century. Modern reconstructions suggest the device likely used an inverted pendulum, suspended delicately to amplify subtle ground movements. When seismic waves disturbed the equilibrium, the pendulum would tilt toward the quake's origin, activating a series of interconnected arms that tripped the corresponding dragon's release mechanism. The precision was staggering. Historical records claim the seismoscope once detected a quake so distant that no one in the capital had felt it, only for messengers to later confirm tremors exactly where the device had indicated. But the seismoscope's brilliance extended beyond mechanics. Its design was a fusion of science and symbolism, reflecting ancient China's cosmic worldview. The 8 dragons aligned with the cardinal and intercardinal directions, mirroring the Bagua, a fundamental concept in Chinese philosophy representing the forces of nature. Even the choice of frogs wasn't arbitrary. In Chinese mythology, frogs were believed to sense impending disasters. Every element served both practical and prophetic purposes, blurring the line between instrument and ritual object. Zhang Heng himself was a polymath, an astronomer, poet, and engineer who saw no division between art and science. His seismoscope wasn't born in isolation but from a lifetime of observing patterns, the sway of hanging lamps during tremors, the behavior of water in jars, even the way wind altered the pitch of vibrating strings. This cross-disciplinary curiosity echoes modern approaches to innovation, where breakthroughs often happen at the intersection of seemingly unrelated fields. Yet for all its sophistication, the seismoscope's legacy is bittersweet. No original survives, only descriptions and later replicas. Some historians speculate it was too advanced for its time, its principles misunderstood or underutilized. Others suggest it may have been a victim of its own success, with later dynasties prioritizing divination over instrumentation. Whatever the reason, the device vanished from history for centuries, a reminder that even the most revolutionary ideas can be forgotten until someone rediscovers them, dusts them off, and realizes the ancients might have been onto something extraordinary all along. Today, as seismologists rely on networks of digital sensors to monitor tectonic shifts, Zhang Heng's invention stands as a testament to a timeless truth. Sometimes, the most profound technologies aren't those with the most components, but those that listen closest to the Earth's whispers. The dragons may be silent now, but their message still echoes. Innovation isn't just about moving forward. It's about recognizing the brilliance that came before. Rising like ancient sentinels above the rooftops of Persia, wind catchers weren't just architectural ornaments, they were climate control systems carved from stone and ingenuity. These towering structures, some reaching heights of 30 feet, harnessed the desert's own breath to transform sweltering interiors into oases of coolness. The principle was deceptively simple. Strategically angled vents at the top captured prevailing winds, funneling them downward through vertical shafts into living spaces below. But the real magic happened underground, where labyrinthine tunnels called qanats intersected with the airflow, passing over subterranean water channels that naturally chilled and dehumidified the air before it entered homes. The result, a passive cooling system so effective interior temperatures could drop by as much as 20 degrees Fahrenheit without a single watt of electricity. What set Persian wind catchers apart wasn't just their functionality, but their adaptability to microclimates. In coastal regions like the Persian Gulf, architects designed multi-directional towers to catch breezes from any angle, while desert cities favored single-directional vents aligned with seasonal wind patterns. Some versions even incorporated damp cloth or ceramic filters to trap dust, an ancient precursor to modern air purification. The most advanced designs, like those in Yazd, featured adjustable internal flaps to regulate airflow like a 4,000-year-old thermostat. This wasn't guesswork, it was fluid dynamics mastered through centuries of observation, where every curve and aperture was honed to exploit the Venturi effect long before the term existed in textbooks. The true stroke of genius lay in their integration with yachtulls, massive ice reservoirs that doubled as thermal batteries. During winter, workers diverted water into shaded pits where it froze overnight. Come summer, wind catchers would draw air over these ice chambers, creating refrigerated storage for perishables, a concept so advanced. Modern engineers now study these structures for sustainable cooling solutions. Imagine a civilization that not only survived extreme heat but thrived in it, turning physics into an art form. Today, as global energy demands soar, wind catchers are experiencing a quiet renaissance. Architects from Dubai to Arizona are resurrecting these ancient principles, pairing them with solar panels to create hybrid systems that use 90% less power than conventional air conditioning. The irony is profound. The same technology that cooled the palaces of Cyrus the Great might one day help curb our reliance on fossil fuels. The Persians didn't just build for their time, they crafted a legacy that whispers across millennia, proving sometimes the most futuristic solutions are hidden in plain sight, etched into the very stones beneath our feet. Carved into the lids of ancient Egyptian coffins, the diagonal star clocks whisper a secret time wasn't just measured by the sun's arc, but by the silent dance of constellations. These intricate tables, etched with meticulous hieroglyphs, weren't mere decorations. They were functional observatories in miniature, allowing priests to slice the night into 12 precise hours, regardless of the season. Imagine standing under a desert sky 3,000 years ago, your eyes tracing the path of a star like Sirius as it crossed an imaginary line in the heavens. Each star's rising marked a new hour, its position shifting slightly with the Earth's rotation, a celestial metronome ticking across the cosmos. What made these star clocks revolutionary wasn't just their accuracy, but their adaptability. Unlike modern clocks that march to rigid 60-minute beats, the Egyptian system acknowledged time's fluidity. Summer nights were shorter than winter ones, so the tables accounted for these seasonal shifts by tracking different decans, groups of stars that rose at 40-minute intervals, 10 days apart. This wasn't a static chart, it was a dynamic algorithm, recalibrating itself as the year unfolded. a priest could consult the coffin lid like a programmer debugging code, cross-referencing the current decan with lunar phases to fine-tune the temple's rituals or the kingdom's agricultural calendar. The genius of these clocks lay in their fusion of astronomy and arithmetic. Each decan's movement was mapped mathematically, with scribes recording their progress across the sky in diagonal rows, a visual representation of time's passage that predated graph paper by millennia. Some tables even included corrections for atmospheric refraction, compensating for the way Earth's air bent starlight near the horizon. This level of precision hints at something extraordinary. The Egyptians didn't just observe the stars, they reverse-engineered the night sky's mechanics, turning celestial patterns into a reproducible formula. Yet the star clock's true brilliance might be their democratization of time. While sundials were useless after dark and water clocks froze in desert cold, these tables worked anywhere, requiring no tools beyond the human eye and a trained memory. Farmers, travelers, and midwives could all use them, their knowledge passed down like a living user manual. The coffin lids themselves tell a poignant story. Timekeeping wasn't just for the living. By inscribing these charts on burial containers, the Egyptians ensured even the dead could navigate eternity's hours, their souls synchronized with the eternal rhythm of the stars. Today, as atomic clocks tick away in underground laboratories, the diagonal star tables remind us that technology isn't about complexity, it's about solving problems with whatever tools lie at hand. The Egyptians didn't need gears or glass to build a world-class chronometer. They had patience, curiosity, and the infinite canvas of the night sky. In a way, their star clocks still function if you know where to look. On a clear evening, far from city lights, those same decans rise right on schedule, proof that some innovations transcend time itself. High in the Andes, where the air thins and the condors soar, the Inca Empire built an administrative marvel without a single sheet of parchment or stroke of ink, the Quipu. At first glance, these clusters of knotted cords dangling from a primary string might resemble elaborate tassels, but unravel their secrets, and you'll find a data storage system so sophisticated, it challenges everything we thought we knew about ancient record-keeping. Each knot, each twist of fiber, even the subtle variations in color and texture formed part of a complex three-dimensional language. Position a knot higher or lower on the string, and you're altering numerical values, a decimal system where clusters represented units, tens, hundreds. Twist the thread clockwise instead of counterclockwise, and you've switched from recording maize harvests to tracking population shifts. This wasn't just accounting, it was binary code woven in wool, a tactile database that could store everything from tax records to epic poetry. Recent breakthroughs have shattered old assumptions that quipus were mere numerical aids. Linguists studying their structures now suspect they might encode syllables or logograms, potentially making them the only known example of a three-dimensional writing system. Imagine a census taker knotting cords to document a newborn's name alongside village grain stores, or a general relaying battle strategies through carefully spaced loops. The implications are staggering. If fully decoded, these threads could reconstruct lost chapters of Andean history, offering voices to a civilization long silenced by colonial erasure. What's most astonishing is how the system mirrored the Inca worldview. Just as their terraced agriculture sculpted mountains into productive harmony, quipus transformed chaos into order through elegant hierarchies. Main cords branched into subsidiaries, creating a physical manifestation of their empire's structure, centralized yet adaptable. Colors held cosmic significance: crimson for warriors, gold for the sun god Intai, green for fertile valleys. Even the fibers themselves carried meaning, with llama wool denoting pastoral data and cotton reserved for sacred events. This wasn't just information storage, It was a tapestry of culture, economics, and spirituality spun into tangible form. Yet the Quipu's true genius lay in its portability and durability. Unlike fragile scrolls or tablets, these cords could be rolled up and carried across treacherous mountain passes by chasqui runners, the Inca's legendary relay messengers. Damp climates that would dissolve paper left Quipus intact. Fires that consumed libraries merely singed their edges. Modern experiments show that even after centuries buried in desert tombs, their knots remain readable, a testament to fiber's endurance as a medium. The tragedy is how much we've lost. Spanish chroniclers noted that in the 16th century, Quipucamayok's keepers of the knots could read them aloud like books, their fingers translating patterns into narratives. But colonial zealots, fearing the system's pagan associations, destroyed thousands, leaving only around 600 survivors. Today, researchers armed with machine learning are racing to crack their code, comparing knot configurations across regions like linguists piecing together a Rosetta Stone. Every decoded chord whispers the same truth. Innovation isn't bound to any one material or form. Whether it's silicon chips or spun alpaca wool, the human drive to record, to remember, to communicate transcends the tools we use to do it. Perhaps the Quipu's greatest lesson is one of humility. For centuries, Western scholars dismissed non-alphabetic systems as primitive, yet here was a civilization that encoded multidimensional data in a format accessible to both sight and touch. In an age where we fret about digital decay, how long will our hard drives last? The Inca offer a quiet provocation. Maybe the future of information lies not in the ephemeral glow of screens, but in the enduring twist of a thread. The roar of water crashing through stone channels mingled with the haunting tones of the world's first keyboard instrument, an ancient fusion of engineering and artistry that would make even modern musicians pause. The Greek hydraulis, born in the 3rd century BCE, wasn't just an ancestor of the church organ. It was a programmable machine where water pressure became the unsung conductor of symphonies. Picture a musician seated before a series of bronze keys, their fingers dancing across the mechanism while beneath them, a labyrinth of pipes and submerged chambers harnessed the relentless flow of water to force air through precisely tuned reeds. The louder the water's rush, the more powerful the sound, a natural amplifier centuries before electricity. What set the hydraulis apart wasn't just its novelty, but its astonishing adaptability. By adjusting water levels in the central tank, players could alter the instrument's pitch and timbre, effectively coding its output like a primitive synthesizer. Historians believe some versions even featured interchangeable sliders or rotating cylinders, early presets that allowed performers to switch scales or modes mid-performance. This level of control was unprecedented. While lyres and flutes relied solely on the player's skill, the hydraulis introduced mechanical consistency, enabling compositions too complex for other instruments of the era. The genius behind its design lay in the marriage of two seemingly unrelated forces, hydraulics and acoustics. A steady stream of water kept air pressure constant in the wind chest, eliminating the breathy inconsistencies of mouth-blown pipes. This innovation didn't just expand musical possibilities, it mirrored principles still used in modern pipe organs and even electronic wind instruments today. The hydraulis was more than an instrument, it was a physics experiment disguised as entertainment, proving that art and technology could intertwine seamlessly. Yet the hydraulis' legacy extends beyond concert halls. Roman emperors reportedly used its thunderous voice to signal gladiatorial combats, its deep tones cutting through arena chaos like a primordial foghorn. Later, Byzantine engineers scaled down the design for portable battlefield versions, their eerie wails demoralizing enemies before the first arrow flew. This adaptability hints at a broader truth. The hydraulis wasn't just a musical tool, but a cultural chameleon, equally at home in temples, theaters, and war camps. Perhaps most fascinating is what the hydraulis suggests about lost knowledge. Surviving descriptions by engineers like Vitruvius reveal intricate details about valve systems and water-to-air ratios, proof that its creators understood fluid dynamics on a level that wouldn't be matched until the Industrial Revolution. Archaeologists still hunt for physical remnants, but the few recovered fragments, like those at Dion in Greece, confirm the descriptions weren't exaggerations. Today, as musicians manipulate digital soundscapes with MIDI controllers, they're walking a path first carved by those ancient hydraulis players. The instrument's spirit lives on in every synth patch that emulates wind instruments or pipe organs, a reminder that innovation isn't always about inventing something new. Sometimes it's about recognizing the brilliance of what came before. The next time you hear the swell of an organ in a cathedral or the pulse of electronic music, listen closely. Beneath the notes, you might just catch the echo of water rushing through a long-forgotten Greek workshop, where art and engineering first learned to dance together. The streets of Pompeii still whisper secrets beneath layers of volcanic ash, but perhaps none are as enduring as the silent revolution embedded in its very walls. Roman concrete didn't just hold stones together. It defied time itself thanks to a recipe so advanced, modern labs are still unraveling its mysteries. While today's concrete crumbles after decades, structures like the Pantheon stand strong after 2,000 years, their resilience rooted in a forgotten alchemy of volcanic ash, lime, and seawater. This wasn't mere mortar, it was a self-healing marvel, engineered to repair its own cracks as water seeped in, triggering chemical reactions that filled gaps with new crystalline growth. Scientists now call it pozzolanic chemistry, but to the Romans it was simply the way things were built, a testament to their uncanny understanding of materials science. What made this concrete so extraordinary was its symbiotic relationship with the environment. Unlike modern mixes that degrade in salt water, Roman maritime concrete actually strengthened when exposed to the sea. Tiny flecks of volcanic tuff, a porous rock from the Bay of Naples, acted like microscopic reactors, their aluminum-rich crystals dissolving slowly over centuries to form a glue-like mineral called strettlingite. This natural time-release mechanism meant the material didn't just resist erosion. It evolved, becoming denser and more resilient with age. Recent X-ray studies revealed how seawater percolating through harbor walls in ancient Caesarea triggered the formation of rare minerals like aluminous tobamorite, creating a lattice structure tougher than steel-reinforced concrete. The Romans had essentially invented a living material, one that adapted to its surroundings like a coral reef. Yet the true stroke of genius lay in their sourcing. Roman engineers didn't just use any volcanic ash, they sought out specific deposits from the Pozzuoli region, where eruptions had created the perfect blend of silica and alumina. This was no accidental discovery. Surviving texts like Vitruvius De Architectura detail precise ratios for different applications, from flexible mortar in earthquake-prone areas to ultra-dense mixes for aqueducts. They even adjusted recipes based on climate, adding horsehair to prevent cracking in cold regions or crushed pottery for extra durability in humid zones. Such meticulous customization hints at an empirical understanding of material science that rivals modern engineering protocols. The tragic irony is that this knowledge vanished for millennia, eclipsed by cheaper, faster alternatives during the Middle Ages. Modern concrete, reliant on Portland cement, prioritizes quick setting over longevity, leading to infrastructure that requires constant repair, but the tide is turning. Researchers at UC Berkeley have successfully recreated Roman-style concrete using fly ash from coal plants, mimicking the self-healing properties of the ancient mix. Other teams are experimenting with bacteria-laced concrete that mimics the Roman model, producing calcite to seal cracks, a clear case of cutting-edge science catching up to antiquity's wisdom. Standing in the shadow of the Colosseum, where travertine blocks still bear the grooves of ancient chisels, one can't help but wonder what other solutions lie buried in the past waiting to be unearthed. The Romans didn't have supercomputers or nanotechnology, but they mastered the art of listening to the earth, turning volcanic fury into architectural immortality. As climate change threatens our modern infrastructure, their concrete offers more than historical curiosity. It's a blueprint for building a world that lasts. The vast Pacific Ocean stretches for thousands of miles under endless blue skies, a desert of water where most civilizations would see only chaos. But Polynesian navigators saw something else entirely, a highway mapped not on parchment, but woven into intricate wooden frames studded with cowrie shells. These weren't mere decorations, they were stick charts, three-dimensional supercomputers of the sea, encoding wave patterns, currents, and the subtle language of swells that could guide a canoe from Tahiti to Hawaii with pinpoint accuracy. What makes these charts extraordinary isn't just their precision, but the fact they weren't meant to be read at sea. Instead, navigators memorized every curve and shell placement before departure, carrying the entire Pacific in their minds like living GPS systems. Each chart was a masterclass in fluid dynamics, crafted from supple palm ribs lashed together to form a skeletal grid. Shells or coral nodules marked islands, while the flecks of the wood mimicked how ocean swells would bend around land masses, a phenomenon modern science calls refraction. Navigators trained for years to interpret these patterns, learning to feel shifts in wave direction through their feet, much like a blindfolded pianist senses a melody in the keys. At night, they'd lie in the hull, detecting currents by how water rippled against their skin. By day, they'd watch the angle of bird flights or the color of clouds over unseen atolls. The stick charts were just the starting point. The real map existed in the navigator's neurons, a cognitive atlas refined through generations of trial and error. What's staggering is the scale of their voyages. Using only these mental maps, Polynesians routinely crossed distances equivalent to London to New York without compasses, sextants, or even a written language to record their knowledge. Their secret lay in understanding the ocean as a living entity. A swell that curved slightly northwest near the Marquesas might straighten near the Tuamotus, a change as recognizable to them as a highway exit sign to us. They even exploited the sea road phenomenon, long, straight waves generated by distant storms that acted as celestial guide rails across the featureless deep. Modern oceanographers have confirmed the stick chart's accuracy with satellite data, discovering that the swell patterns they encoded align perfectly with sonar readings. Yet the chart's true genius was their adaptability. Unlike paper maps that become obsolete, Polynesian navigators could update their mental models in real time, incorporating new discoveries or shifting currents. When European explorers first reached the Pacific, they marveled at how islanders could find specks of land across thousands of miles. The answer was in those knotted frames, not just tools, but a testament to human ingenuity's ability to turn nature's chaos into a navigable system. Today, as we rely on satellites for every turn, the stick charts whisper a humbling truth. Sometimes the most advanced technology isn't made of silicon, but of memory, observation, and a profound dialogue with the world's rhythms. The Polynesians didn't conquer the Pacific with brute force. They listened to it, learned its grammar, and wove that knowledge into something as simple and profound as a shell on a stick. Buried beneath the sands of ancient Mesopotamia, a cracked clay tablet holds the key to a mathematical breakthrough that would shape the modern world. The sieve of Eratosthenes, often credited to the Greek scholar 800 years later, actually appears in Babylonian cuneiform texts dating back to 200 BCE, a sophisticated algorithm for finding prime numbers etched into damp clay with a stylus. But this wasn't just abstract number theory scribbled by scholars. It was mathematics forged in the fires of necessity, a tool as vital to Babylonian life as the plow or the sundial. Picture an accountant in the ziggurate's shadow, fingers flying across the tablet as he calculated interest rates for grain loans, his calculations relying on primes to ensure no merchant could cheat the temple's ledger. What made the Babylonian approach revolutionary was their sexagesimal base 60 system, a choice that still echoes in how we measure time and angles today. Unlike our base 10, which divides neatly by 2 and 5, 60 can be split by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30, making complex fractions startlingly simple. This numerical flexibility allowed them to perform calculations with fractions that would stump later civilizations using clunkier systems. Their tablets don't just list primes, they reveal an intricate understanding of divisibility rules, square roots, and even early algebraic concepts, all organized with a clarity that suggests these methods were standardized across the empire. The genius of their prime number sieve lay in its brutal efficiency. Starting with a list of numbers, the algorithm would systematically eliminate multiples of each prime, leaving behind only the indivisible numbers, a method so elegant, modern computers still use variations of it for cryptography. But here's what's truly astonishing. The Babylonians didn't stop at identifying primes. They used them practically, encoding them into construction ratios for canals and temples, or calculating compound interest for silver loan. A tablet from Lhasa even shows primes employed in inheritance divisions, ensuring land could be split fairly among heirs without fractional plots. Yet the real marvel is how their system transcended mathematics. That base 60 framework became the scaffolding for their astronomy, allowing them to track Venus's cycles with jaw-dropping precision. Their celestial observations, recorded in primes and sexagesimal fractions, laid the groundwork for the zodiac and our modern 60-minute hour. When you check your watch or navigate by degrees, you're unwittingly paying homage to Babylonian accountants who turned river clay into the world's first computational hardware. What we dismiss as ancient arithmetic was actually a paradigm shift. The moment humanity realized numbers weren't just for counting, but for shaping reality. The Babylonians didn't have silicon chips, but their clay tablets were the original hard drives, storing algorithms that would outlast empires. In a world where we fetishize digital innovation, their legacy whispers a quiet truth. Sometimes the most transformative technologies aren't those that flash and beep, but those that endure, silent and unyielding, in the stuff of the earth itself. High in the Himalayas, where the air thins and the winds howl through mountain passes, Tibetan monks harnessed the very elements to power their prayers, not with whispered words, but with spinning cylinders of sacred text. These prayer wheels, often mistaken for simple ritual objects, were in fact meticulously engineered spiritual machines, their hollow interiors packed with tightly wound scrolls inscribed with thousands of mantras. Each rotation, whether turned by hand, flowing water, or gusting wind, sent these encoded blessings spiraling into the universe like divine data packets. But this wasn't just blind faith, it was a fusion of mechanical precision and metaphysical intention, where physics and spirituality became indistinguishable. The largest of these wheels stood taller than a house, their massive copper drums balanced on axles so finely crafted they could turn for hours with just a gentle push. Smaller versions lined monastery walls, connected by intricate systems of belts and pulleys that transformed a single monk's movement into a synchronized chorus of spinning scripture. Yet the true innovation lay in the autonomous design's wheels placed in rushing streams where water's relentless flow became the engine of endless prayer, or vertical turbines catching mountain winds to keep the mantras circulating day and night without human intervention. Imagine walking through a valley centuries ago, hearing the metallic whisper of 100 wheels turning in the breeze, each rotation another ripple in what monks called the Great Web of Compassion. What modern eyes might dismiss as superstition reveals startling parallels to today's technology. The prayer wheel's logic mirrors core computing concepts, stored data the mantras, processing power the spinning motion, and output the dispersed prayers. Just as algorithms run silently in the background of our devices, these wheels perform their sacred calculations continuously, their spiritual code etched not in silicon but in ink and parchment. Some scholars argue they represented an early form of automation, not to replace human labor, but to amplify human intention beyond physical limits. The engineering challenges were profound. Wheels had to balance perfectly to spin smoothly yet contain enough mass to maintain momentum. Scribes perfected waterproof inks for riverside installations, while artisans developed bronze alloys that wouldn't crack in freezing temperatures. The most advanced models even incorporated flywheels and counterweights to regulate speed, preventing violent spins that might tear sacred texts. This wasn't crude craftsmanship, it was precision engineering in service of the soul. Perhaps most fascinating is how the prayer wheel's design reflects Buddhist cosmology. The circular motion echoes the wheel of samsara, the cycle of rebirth, while the endless repetition of mantras embodies the concept of impermanence. Even the materials held meaning: copper for conductivity, spiritual energy; yak leather for durability, endurance of teachings; and vermilion paint representing the life force. Every technical choice carried layers of symbolism, blurring the line between tool and talisman. Today, as apps count our daily steps or remind us to meditate, we're reinventing what the Tibetans mastered centuries ago, using technology to extend our better intentions into the world. The hum of a prayer wheel and the ping of a mindfulness notification share the same aspiration: to weave the sacred into the fabric of everyday life. Only now are we beginning to understand what the monks knew all along: that repetition isn't empty ritual, but the very mechanism through which the abstract becomes real, one revolution at a time. The Aztecs didn't just farm the land, they reinvented it, crafting entire floating worlds where corn grew taller than warriors and beans climbed skyward like living ladders. In the heart of Lake Texcoco, where modern Mexico City now stands, their Chinampas transformed shallow marshlands into the most productive agricultural system of the ancient Americas. These weren't simple rafts of soil, they were meticulously engineered hydroponic islands, built up from the lakebed in precise layers that turned stagnant water into a self-sustaining food factory. Picture a grid of rectangular plots, each about 30 meters long, anchored to the lake bottom with willow trees whose roots wove through the structure like nature's rebar. What made Chinampas revolutionary was their closed-loop ecosystem. Workers dredged nutrient-rich muck from the lake bottom, piling it onto woven reed mats until the plots rose a meter above the waterline. But the real genius lay in the vertical stacking. Charcoal from burned crop waste formed a filtration layer beneath the topsoil, while the surrounding canals provided constant irrigation and a home for fish whose waste fertilized the crops. This wasn't just farming, it was biomimicry at its finest, creating a symbiotic relationship between land and water that required no artificial inputs. Modern tests show these plots yielded up to 7 harvests per year, outperforming even today's most advanced greenhouses. The Aztecs didn't stop at passive productivity. Their Chinampas incorporated active innovations that would impress modern agronomists. Narrow channels between plots acted as thermal regulators, absorbing sunlight by day and releasing warmth at night to protect against frost. Farmers planted ahujot trees along the edges not just for stability, but to attract pollinators and birds that controlled pests naturally. Some Chinampas even featured adjustable gates to regulate water flow between plots, a primitive but effective form of hydroponic control. The result was a system so efficient, historians estimate it fed 200,000 people from just 12 square kilometers, a yield comparable to industrial agriculture, but without the ecological toll. Perhaps most remarkably, Chinampas required no fallow periods. While European farmers struggled with exhausted soil, Aztec plots grew more fertile with each harvest. The secret, their canals doubled as compost tea factories. Aquatic plants like duckweed and azolla, nature's nitrogen fixers, were routinely dredged and mixed into the soil, while human waste from nearby settlements was composted into rich fertilizer. This circular economy turned waste streams into resources centuries before the term sustainability entered our vocabulary. Today, as climate change threatens global food security, Chinampas are experiencing a quiet revival. Scientists have discovered their layered design naturally filters heavy metals from contaminated water, while urban farmers from Xochimilco to Brooklyn are adapting their principles for rooftop gardens. The Aztecs didn't have the word hydroponics, but their floating farms prove ancient solutions often hold the keys to modern problems. In a world racing to develop high-tech vertical farms, sometimes the most cutting-edge technology is the one that's been floating right beneath our feet for centuries. Towering over Prague's Old Town Square, the Orloj doesn't just tell time. It unfolds the cosmos in a symphony of moving brass and painted saints. This medieval masterpiece, built in 1410, isn't merely a clock face but a sprawling mechanical universe, where apostles parade past death's tolling skeleton and the moon's phase shifts with lunar precision. What makes it revolutionary isn't the spectacle, though, it's the labyrinth of gears hidden behind that gilded facade, each tooth and pinion calculating planetary positions with a complexity that rivals modern astronomical software. The Orloj's true genius lies in its dual nature, a theatrical marvel for the masses and a clandestine supercomputer for scholars. At its heart beats the mechanical equatorium, a system of interlocking disks that model the irregular orbits of the sun, moon, and planets as they were understood in the Middle Ages. Unlike simple clocks that track hours, this mechanism accounts for Ptolemy's epicycles, those looping paths ancient astronomers used to explain retrograde motion. One gear train advances the sun's hand uniformly, while another superimposes the wobbles of Earth's tilted axis, creating the shifting sunrise points we call the annelma. The moon display goes further, incorporating an intricate differential gear, a concept not formally described until the 19th century, to replicate the moon's speeding and slowing during its elliptical orbit. This wasn't just ornamentation, it was pedagogy in motion, turning abstract celestial mechanics into something townsfolk could witness daily. But the Orloj was far from alone. Across Europe, cathedral cities competed to build ever more elaborate horological wonders. Strasbourg's clock, completed in 1574, featured a rotating calendar that corrected for leap years and a mechanical rooster whose crow marked solar noon. In Lund, Sweden, a 14th century clock's astrolabe dial could locate constellations for any date, a portable planetarium carved from oak and iron. These weren't vanity projects, they were the medieval equivalent of NAS, a mission control, centralizing astronomical knowledge for agriculture, navigation, and even medical astrology. Monks might consult them to time bloodletting procedures, while merchants used their tide indicators to plan shipments. The most astonishing aspect, their durability. Prague's Orloj has survived fires, wars, and Nazi bombardment, its original gears still meshing smoothly after 6 centuries. Modern engineers have discovered that its brass alloys were specially formulated to resist wear, while its bearings used a lost wax casting technique that minimized friction. This wasn't just craftsmanship, it was material science centuries ahead of its time. The clockmakers even accounted for metal expansion on hot days, leaving microscopic gaps in the gear trains that closed to perfect alignment as temperatures rose. Yet these clocks' true legacy isn't in their mechanics, it's in their vision. They embodied a worldview where time wasn't an abstract grid, but a living tapestry woven from celestial rhythms and human rituals. When the Orloj's apostles appear at the hour, they're not just performing, they're reenacting the medieval belief that heaven's order could be mirrored on earth through ingenuity. Today, as atomic clocks tick away in underground labs, these creaking marvels remind us that technology's highest purpose isn't just precision, but wonder. Every whirring gear, every painted saint whispers the same truth: to measure the heavens is to touch the divine. In the hands of a medieval Islamic scholar, the astrolabe wasn't just a tool, it was a handheld universe, its brass plates etched with the secrets of the cosmos. This intricate device, often no larger than a dinner plate, could calculate prayer times, predict star positions, and even determine the depth of wells with startling accuracy. At its core lay the rete, a rotating star map cut like lace from metal, its delicate pointers marking the brightest stars while a fixed plate beneath represented the celestial sphere. But what set Islamic astrolabes apart was their modular design. Unlike their simpler Greek predecessors, these instruments came with stacks of interchangeable plates, each calibrated for different latitudes from Cordoba to Baghdad. Swap one plate for another, and suddenly the same device could answer astronomical questions in Mecca or Marrakesh, a feat akin to reprogramming a modern computer by sliding in a new circuit board. The astrolabe's true brilliance lay in its ability to condense complex mathematical operations into physical movements. Turning the rete simulated the night sky's rotation, while scales along the edges solved trigonometric problems visually. Need to find the sun's altitude at dawn during Ramadan. Align the rule with the date, rotate the rete until the sun marker touches the horizon line, and read the result. It was analog computing at its finest, transforming abstract calculations into something you could hold and manipulate. Surviving manuals describe over 1,000 uses, from surveying land to mixing medicines at astrologically auspicious moments. One Persian text even explains how to calculate the optimal time for bloodletting by correlating the moon's position with zodiacal charts engraved on the back. What's often overlooked is how these devices democratized knowledge. While European astronomy remained cloistered in monasteries, Islamic makers produced astrolabes in brass, wood, and even paper for students, travelers, and farmers. The 9th century scholar Al-Khwarizmi, whose name gives us the word algorithm, wrote step-by-step guides so clear that modern engineers have recreated working instruments from his descriptions. This wasn't just precision engineering, it was open-source science centuries before the concept existed. The most sophisticated models, like those crafted by Al-Zarqali in 11th century Toledo, incorporated gear trains to model planetary motion. a direct precursor to the mechanical clocks that would later revolutionize Europe. Others featured adjustable Qibla indicators pointing toward Mecca from any location, blending faith with function. Today, as we swipe through smartphone apps that track stars or prayer times, we're unknowingly echoing the astrolabe's legacy. Its genius wasn't just in solving problems, but in proving that the universe's complexities could be held in your palm if you knew how to look. Along the rice paddies of ancient China, where water meant the difference between feast and famine, engineers devised a machine that turned human motion into liquid lifelines, the chain pump. Picture a treadmill powered by farmers' steady footsteps, their weight driving an endless loop of wooden boards through a trough. As each plank emerged from the water, it carried its precious cargo upward before tipping at the apex, sending streams cascading into irrigation channels with rhythmic precision. This wasn't just manual labor, it was mechanical alchemy, transforming muscle into hydraulic force with an efficiency that would inspire industrial revolutions centuries later. What set the chain pump apart was its elegant simplicity. Unlike bucket wheels that lost water between dips or screw pumps limited by their angle, the chain pump's continuous loop of square pallets created an unbroken flow. Oxen could be harnessed for larger versions, their circular path converted into vertical motion through a series of interlocking gears, an early example of torque conversion that modern engineers would recognize instantly. The genius lay in its scalability. Small versions could be operated by a single child treading a bamboo wheel, while massive imperial models stretched over 30 feet high, lifting water from rivers to fortresses atop sheer cliffs. The pump's legacy echoes in places you'd least expect, those moving staircases in shopping malls. Their escalator treads follow the same principle of continuous plates on a rotating chain. Factory conveyor belts carrying everything from car parts to chocolate bars owe their DNA to those ancient wooden slats gliding through water. Even roller coaster lift hills use a direct descendant of this technology, where chain-driven hooks engage with train undercarriages, proof that 4th century Chinese farmers were unwitting pioneers of theme park thrills. But perhaps the most revolutionary aspect was its democratization of power. While Roman aqueducts required slave labor and centralized control, chain pumps empowered individual villages. Farmers could maintain and repair them with local materials, adjusting the number of treaders or oxen based on need. Surviving Ming Dynasty manuals describe modular designs where damaged sections could be replaced without dismantling the entire system, a lesson in sustainable engineering we're still relearning today. Modern tests reveal just how advanced these machines were. Replicas can lift water over 15 vertical feet while losing less than 20% of their energy to friction, a staggering efficiency for pre-industrial technology. The secret lay in the precise spacing of the pallets. Too close, and they'd drag against the trough. Too far apart, and water would spill back. Trial and error over generations honed these ratios into something approaching mathematical perfection, all without a single equation being written down. What began as a solution for rice irrigation quietly shaped the trajectory of mechanical design. From the dockside cranes of medieval Europe to the assembly lines of the Industrial Revolution, the chain pump's DNA is everywhere we've needed to move things smoothly, continuously, efficiently. Its creators could never have imagined their wooden contraption would one day influence how we board airplanes or manufacture smartphones. But that's the nature of true innovation. It ripples outward in ways no single mind can predict. The next time you step onto an escalator, pause for a moment. Beneath the steel and electricity, you're riding an idea born in the muddy fields of ancient China, where water climbed mountains one wooden plank at a time. Inside the dimly lit chambers of Renaissance studios, a quiet revolution unfolded, one where light itself became the artist's most obedient apprentice. The Camera Obscura, a deceptively simple device, transformed darkened rooms into living canvases, where bustling market squares or sun-dappled landscapes projected themselves upside down through a tiny aperture. Artists like Vermeer and Canaletto didn't just sketch from life, they traced reality's fleeting impressions with uncanny precision, their brushes chasing the play of light on walls like scribes transcribing nature's own handwriting. This wasn't cheating, it was optics harnessed as a creative tool, bridging the gap between observation and imagination centuries before the first photograph. The magic lay in the physics. When sunlight streamed through that minuscule hole, it carried with it an inverted image of the outside world, conforming to the same principles that govern modern cameras. The smaller the aperture, the sharper the projection, though dimmer, a trade-off Renaissance artists learned to manipulate by adjusting shutters or lenses placed in the opening. Some studios even employed rotating mirrors to redirect light, allowing painters to compose scenes without moving their canvases. The result, paintings with near photographic perspective, where every cobblestone receded into the distance with mathematical perfection, and shadows fell exactly as physics dictated. But the Camera Obscura's influence went beyond technical accuracy. It fundamentally altered how artists saw the world. Suddenly, they could study the way light fractured through glass or how fabric folds caught highlights, details too fleeting for the naked eye to hold. Vermeer's luminous interiors, with their jewel-like reflections and soft diffused glow, bear the unmistakable fingerprint of this device. His girl with a pearl earring isn't just a portrait, it's a masterclass in observing how light wraps around form, a lesson learned under the camera's patient tutelage. What's often overlooked is how these darkened rooms doubled as experimental labs. Leonardo da Vinci filled notebooks with observations about the camera's behavior, sketching its projections alongside studies of human vision. He realized the eye itself functions like a camera obscura, an insight that would later inspire the development of artificial lenses. By the 17th century, portable versions emerged, ancestor to today's DSLR, with folding tents or handheld boxes allowing artists to capture scenes anywhere. Canaletto's sweeping Venetian vistas, so precise they were used as historical records, owe their existence to these mobile units. Yet the Camera Obscura's legacy isn't confined to art. Its principles underpin everything from modern projectors to smartphone cameras, proving that sometimes the most transformative technologies begin as simple acts of observation. The Renaissance didn't just give us masterpieces, it gave us a new way to see, one where science and art conspired to freeze light itself onto canvas. Every time you snap a photo today, you're stepping into that same darkened room where a tiny opening still holds the power to capture worlds.